here is some extra practice with var of par, but also to show you that you can use this technique to solve second-order linear ODE that are not constant coefficients, just to show how powerful this is. In particular, let's try to solve t squared y double prime minus 2y equals 3t squared minus 1. And for this, assume that t squared and 1 over t solve the homogeneous equation. That will be given to you, but if you're curious, what you can do, you can assume what the solution is a power of t and find the powers to be 2 and 1 minus 1 to get t squared and 1 over t. But again, beyond the scope of this course. And for this, in order to apply var of par, remember the stuff students lose lots of points on, which is to put this in standard form. Again, we want the coefficient of y double prime to be 1, but here it's t squared. So let's divide this by t squared. So y double prime minus 2 over t squared y equals 3t squared minus 1 over t squared. So it's simply 3 minus 1 over t squared. So here all we did, we divide by t squared. And now, what we want now is the homogeneous solution. Homogeneous solution. Well, we know that t squared and 1 over t solve the equation, the homogeneous equation. This is like saying e to the 2t and e to the 3t solve the homogeneous equation. So the homogeneous solution is just a linear combination of those two. So it's just a times t squared plus b times 1 over t. This technically requires more justification about second-order ODEs, which requires a whole chapter about Wronskian, but here we take that as a given. So once again, t squared and 1 over t are building blocks, so the homogeneous solution is just a linear combination. Now, what we want to do now is do actual var of par, meaning that suppose a particular solution is u of t times t squared plus v of t times 1 over t. And we want to apply the var of par equations. Par equations. Which is simply, so you put t squared and 1 over t in a matrix, and you differentiate. So 2t minus 1 over t squared, that's our matrix. Then the vector is u prime and v prime. And you put 0 and the inhomogeneous term, which, careful, it's not 3t squared minus 1, but this new thing, 3 minus 1 over t squared. Or t squared. And then you just solve this using Kramer's rule. So step 4. Kramer rule. So remember how to do this. U prime of t is the ratio of two determinants, one being, or the denominator being, the determinant of the matrix itself. So t squared 1 over t, 2t minus 1 over t squared. And for the numerator, you replace the first column by the inhomogeneous term. So 0, 3 minus 1 over t squared. And the second column is unchanged. So if we look at this, 1 over t minus 1 over t squared. Minus 1 over t squared. I know it's a little bit messy here. Erase this. Now, as complicated as this looks, take advantage of the zeros. So 0 times minus 1 over t squared, and then minus 1 over t, and then 3 minus 1 over t squared, divided by t squared times minus 1 over t squared, minus 1 over t times 2t, and this then becomes, so 0, I think, minus 3 over t, and then plus 1 over t cubed, if I'm not mistaken. Yeah. And then divided by, so this becomes minus 1, minus 2, so this becomes minus 3. So in particular, u prime becomes 1 over t, and then minus 1/3 t to the minus 3, if you wish. Okay. That's one thing. And then for v prime of t, same thing. So the denominator is minus 3. And then for the numerator, you replace now the second column by 0 and 3 minus 1 over t squared. Bit easier here. So t squared and 2t, and then 0. Zero, and then 3 minus 1 over t squared. Right, which becomes t squared times 3 minus 1 over t squared minus 0 over minus 3, which then becomes 3t squared minus 1 over minus 3. And so that becomes minus t squared plus 1/3. Very good. So that is v prime of t is minus t squared plus 1/3. And the next step is to integrate. That's not what I wanted. So step 5. So u prime of t, remember, was 1 over t minus 1/3 t to the minus 3. So u of t is the integral of that, integral of 1 over t minus 1/3 t to the minus 3 dt. And remember, integral of 1 over t is ln of absolute value of t, and this becomes minus 1/3 t to the minus 3 plus 1, so minus 2 over minus 2, and that becomes ln of t, and I believe plus 1/6 t to the minus 2. That was for u prime. Now for v prime, so that was the hard part. Now the next part is a bit easier. So v prime was minus t squared plus 1/3, and so v of t is the integral of minus t squared plus 1/3 dt, which is minus 1/3 t cubed plus t over 3. And again, no plus c's because we just want one particular solution. Okay, and now that we found u and v, we can find our particular solution. So yp of t was u of t times t squared plus v of t times 1 over t. And that is ln of t and then plus, can write this as 1 over 6t squared times t squared, and then plus v of t. So I think minus t cubed over 3 plus t over 3 times 1 over t. Now, sometimes I may ask you to simplify this, which usually just means expand it out. So this becomes t squared ln of t plus 1 over 6 minus t squared over 3 plus 1/3. Now notice the 1/6 and the 1/3 simplifies, and in the end we just get t squared ln of t minus t squared over 3 plus 1/2. And that was a particular solution. Now for the general solution, so I believe step 6, we then get our general solution, y of t equals y0 of t plus yp of t, and that is, I believe, at squared plus b over t plus t squared ln of t minus 1/3 t squared plus 1/2. If you leave it in this form, you would get full credit. But if you want to simplify this just a little bit further, notice here we have at squared, and here we have minus 1/3 t squared. Since a is arbitrary, this minus 1/3 actually goes into a. So this is the same thing as saying at squared plus b over t plus t squared ln of t plus 1/2. So once again, this is because a is arbitrary. And that finally gives us our solution here. And again, I know this looks complicated, especially the first couple of times you do it, but this is really one of those techniques that the more you do it, the more you see that it's always the same thing. And once again, the good news is you do not need to think about any exceptions. So in particular, don't even think about resonance in this example. Thank you very much.